We all know what it's like to be under pressure, but did you know you can actually measure it? You might remember this equation from physics, P equals F over A. This would be in kilograms divided by meters times seconds squared. It's the units. And we can visualize a little bit like this. Let's sort of see a little box like this. This box right here, he's not under any pressure. He's under low pressure, this guy right here. But let's say you put some stuff in that box. We're going to put gas. 10 molecules of gas in that box, and at that point those molecules are going to be kind of moving around and stuff and touch the sides of the box, and they're going to press on the sides of the box. So when they do that, they're going to basically press out in this direction, causing pressure. And well, that means that this guy's under high pressure and that guy's under low pressure. There's a whole bunch of units of pressure. That would be 1 atm is going to convert to 760 torr, which is the same as 760 millimeters of mercury. That's going to equal 101.325 kilopascals, which is going to equal 1.01325 bar. Those are very similar types of units there. And 14.7 psi, that's in your car tires. I've drawn here a barometer, which is essentially a tank filled with mercury, and a test tube also filled with mercury, but it's inverted in there. Now, what happens is the pressure from the outside air is pushing down here on the liquid in the tank, and then the liquid is rising up in here because, well, it's going to push up through that. Now, 760 millimeters is the natural height that mercury will rise. So when we look at this barometer here, we must know that inside of this little space, there's going to be a 0 torr vacuum. But that gives us something interesting, because when we can look over here, imagine if we had a gas inside of this vacuum and it started pushing down, that it would actually cause the mercury to shrink down and become only maybe 260 millimeters. And so we'd be able to calculate the difference there, and we would be able to find that there is a 500 torr gas inside of this, inside of that barometer. Now let's compare what happens at a high altitude versus a very low depth. But first we should know that, like, high density, this stuff is going to sink, basically go down to the floor. Whereas on the reverse side, if something is low density, then it would essentially float. So you would have low density stuff. And this is kind of going to happen in either direction. So the heavy things are going to sink down to the bottom of the ocean and float to the top, versus things that are sort of lighter gases are going to float into the sky, and the heavier gases will also sink towards the ground. So this will happen both in the air and in the water. Now, when it comes to the density of a gas, we need to consider the molar mass. So if the molar mass goes up, the mass will go up, then the density will also go up. And if the temperature goes down, then the molecules, the particles aren't going to be moving quite as much. They're going to slow down and therefore take up less space because they're not going to move around as much. So that means the density will also go up. The molar mass goes up, the temperature goes down, the density goes up. Now let's consider the containers that these gases might be in. So let's say we go to a really high density area down here. Then what's going to happen is the container is essentially going to be smushed. There's all this stuff pushing against it, and it's going to shrink the container inside of there. And this is going to be high pressure, because this stuff is going to be compressed. But if we go to the higher altitudes, the lower densities up here, we're going to find that container will actually expand, because there's not going to be as much stuff out here pushing on it. So this stuff will expand, and this will cause lower pressure up here. So that's the difference between the altitude and the depth. There's this thing called STP, or standard temperature and pressure, which would mean that the temperature is 0 degrees Celsius and the pressure is 1 atm. So we have right there. This is standard temperature and pressure. And we could also calculate 1 mole of gas at STP. We could determine that to be 22.4 liters. Okay, which is essentially kind of an interesting conversion factor. So let's say we were given the volume in liters of a gas. We could actually use the molar volume, which is this thing right here. So we'll put the mole of gas on top, and we'll put the 22.4 liters on the bottom, so these things will cancel. And this is called molar volume, and it's similar to the molar mass, but the molar mass would be something like this. You got the mole of gas over here versus the grams on this side, and so that would be more of the molar mass. Now, the way we calculated that was by using the ideal gas law. And so that would essentially be PV equals nRT. V is actually going to be the container volume here. Now, this equation is going to work under certain conditions. First off, you might need to have low pressure. The reason for that is because, well, the particles are going to have a certain size, and the container is going to have a certain volume. And so that ratio needs to be very, very small, because you don't want too big of particles in a small container. That would be high pressure, so you kind of want the opposite, okay? And you also want this to happen under high temperature conditions, because that way the kinetic energy of the temperature is going to be greater than the intermolecular forces that are sort of holding these gas particles together and things like that. So you want that, and you would also want a dilute gas, so that way the particle distances are far enough apart. So these are sort of a couple of different things that would make the ideal gas law work properly. Now, I've written this value of R a whole bunch of times. It's going to be that constant right there. And this is just because, well, we have a bunch of different uses of pressure, so they're all going to kind of match to whatever unit of pressure you kind of need. Something interesting to note over here, this is in joules. Well, it turns out that joules is actually kilograms times meter squared over second squared. It's actually very similar to what we have over here for pressure. So if we actually multiply pressure times volume, we actually get joules. Now there's another value of R that's kind of interesting. You might recognize R equals 6.022 e to the 23rd. That's Avogadro's number. But let's multiply that times the Boltzmann constant. This is the R that you would use in here if you're calculating the moles of a gas. But if you want to calculate this stuff for the particle, for an individual particle, you can actually replace this with the Boltzmann constant, which is 1.381 e to the negative 23. This is joules over K. And so you can kind of see how the moles is basically taken out because it's Avogadro's number. So this is the Boltzmann constant, which you can use for particles instead of moles. Particles. Now, two more important things. Let's look at all the units of this. So obviously the volume of the container is going to be in liters. The pressure is going to be either in ATM or something like that. The temperature is always in Kelvin. We have these K's over here. And this N is the number of moles, and the volume, of course, is of the container, not of the gas. So that should take care of the units there. Our goal is essentially to kind of calculate either the pressure or the volume or the moles or the temperature of these things. But let's take a quick detour before we go into more of that stuff. Because we can rewrite this formula a little bit more like that, right? And I can also say that mass divided by the molar mass is equal to the moles, which in this case is just the letter N. So I can actually replace that and put something like this: mass divided by the molar mass, throw in the volume, throw in the RT that we have, and then I'll notice that mass divided by volume is just density. So density times RT divided by the molar mass is also another way that we can kind of get some more information from this equation. This equation is just going to help us get a lot of information about gases, and it works very well under these three conditions. Now let's just get into the A, B, C, D, F, G's of gases, which are essentially just all the 7 laws you really need to know about gases. There's not too much more after that. We'll start with Avogadro's law. So he basically set P equals 1 and T equals 1, and if we do that in this equation, we get something like this: V1 over N1 equals R. We can kind of rearrange these equations slightly by putting the N on that side. And if we have that situation happening, we can actually set that equal to V2 over N2, because no matter what you do with these variables, they're always going to equal R, so you can kind of switch them up, and they're always going to be at that particular ratio that is perfectly going to equal R. So this is Avogadro's law, and what it says is if we have a mole of gas right here, it's kind of a small amount of it, then you're just going to have a small amount of volume. A small mole, small volume. But let's say you have a huge moles, lots and lots of moles of that stuff. So as the moles increase, so does the volume. That's what this equation is trying to say. The next law is Boyle's law. And so he decided to set n equal to 1 and t equal to 1. And he came up with this equation, P1 V1 equals R. And he set that equal to, well, if you switch those things around, no matter what, you're always going to get the same ratio that will equal R there. And what this law is essentially trying to say is, let's say we had a pretty big volume here. Okay, there's not too much pressure going on here, just a little bit. This is going to be, if the volume goes up, the pressure is essentially going down. So you got enough space in there. But you take that same amount that we had in there, it was only 10 dots, and look at how more packed that is. So that pressure is going to be much greater over here. As the volume goes down, the pressure goes up. And that is Boyle's law. Now let's look at Charles' law. This is the C. Now he decided to set n equal to 1 and p equals to 1. And so he came up with this situation, V1 divided by T1, set that equal to R, change that however you want, but you're always going to come up with the proper ratio that will always equal R. And so what this is implying is that, okay, let's say you have, a bit of gas there in that particular space. And this is at a low temperature. So the volume is relatively low. But let's say we increase that temperature. These things are going to move around quite a bit and create, that volume is going to increase because those things are moving around so much. So basically, as the temperature goes up, the volume goes up as well because of the movement of those particles. That's Charles' law, ABC so far. Now Dalton's law takes us in a little bit of a different direction. Let's say we had the sum of a whole bunch of pressures. Now you can kind of think of this as being something like this. Let's say we had a couple of H2O molecules, and these were in liquid form. And then they suddenly sort of evaporated and became gas. So this is going to be plus O2 gas. So you kind of have two hydrogen molecules, one oxygen molecule, and they're kind of floating around as gas particles. Well, for that same reasoning, you actually can say, okay, well, I actually would have 2 moles of the H2 gas, and I have only 1 mole of the O2 gas. That is the ratio between these. So you're finding out that the pressure inside of this, the pressure of those particular gases, there has to be 66% pressure from the H gas, and it has to be 33% pressure from the O2 gas. Well, because it's the same container, these are obviously going to be under the same conditions, and so therefore the pressure exertion is going to be sort of the same. So it just depends how much you have of each particular gas, since it's ratioed based off of how much you have. So now what you can do is actually you can take that percentage and just multiply it by the total pressure, and you'll be able to get the partial pressure of the H, or the partial pressure of the oxygen. So that's kind of cool. And one last thing to remember about the partial pressures is that if you're ever collecting a gas over water, you must remember to subtract the partial pressure of that water at the particular temperature and stuff in order to get the partial pressure of the gas, because there's always going to be water vapor inside of that if it was collected over water. So you just have to subtract the water vapor from that to get the pressure of the gas. So far we've had A, B, C, and D. Now let's take a look at E, which is the effusion law. And so that's basically like, let's say we had this little hole, and we had some streams of gas and stuff, and they're basically streams of particles that are basically being pushed through this hole, and kind of turn into one stream at the end over there. Usually we're going to be comparing the speeds of two gases going through the same type of hole. So we would basically say that the time of the gas A divided by the time of the gas B is going to be essentially this ratio between the molar mass of A divided by the molar mass of B under the square root. But we could also think of this as rate. Now rate is going to be essentially liters per second in this particular situation. But we could also think rate of A divided by rate of B, and we could also set up another ratio over here. Molar mass of B divided by the molar mass of A. So this is the effusion laws. Now we'll take a look at F. For the F, we have the Fick's law. And Fick's law of diffusion, there isn't really going to be a formula for this, but if we have a dense area here that has a whole bunch of stuff, then naturally it's going to want to start to spread into this area over here that doesn't really have a lot of stuff. So that's going to be called the Fick's law of diffusion. We can think of this as equalization over time. Now for the final law of gases, G, we can actually go to the Gay-Lussac's law. And he basically decided to set n equals 1, v equals 1. And so now we can rearrange that equation and we can get P divided by T equals R. And no matter how you rearrange that, you'll always get the same ratio. So P2 over T2 is also going to be equal to R. And what this is implying is, let's say we had the same volume here and the same amount of gas too. But the temperature is increasing, so those things are going to be moving around quite a bit in there. Obviously that's going to cause a bit more pressure on this side. And so this would be like at 100 degrees, this would be more at 0 degrees. But you can see how if the temperature goes down, then the pressure goes down. And if the temperature goes up, then the pressure also goes up. And it's essentially for the same reason that the volume has that same kind of relationship. And of course it makes sense because look, both of those are on that side, so the temperature's on that side. Those things are related. So those are going to be the A, B, C, D, E, F, G's of gases. These are almost all the laws that you actually need to know about gases. We're almost done here. Well, let's go back to this thing that was in joules over here. And let's remember that joules was energy, and energy, it's actually kinetic energy. It's the kinetic energy of the particles moving around. And they're going to actually hit each other. So there's going to be an average travel distance between these perfectly elastic collisions. And we can actually calculate that. We call this thing called the mean free path. So let's say the particles are kind of just going like this, back to back. It's the mean free path. And it makes sense that if the mean free path is decreasing, then that means that the pressure is actually increasing because things are hitting against each other faster and more often. Well, we could basically say that as the distance increases, the pressure will decrease. So this is the mean free path. And we can actually create an equation to calculate this by saying lambda equals the volume, and this is going to be in meters to the third. Divide this by 4 pi squared 2 r squared times n. Well, the volume is the volume of the container itself, not the gas. The r is going to be the radius of the gas molecules. And the n is going to be the actual number of molecules. Obviously, there's going to be some sort of velocity associated with this, and because there's negative velocities involved as well, because things are going forwards and backwards, we need to use the RMS. That's the root mean squared. So what we're going to do is we're going to take the sum of all the particle velocities. And since some of them are negative, we're going to square them, and then we'll just take the sum, and then we're going to take the square root. So that is the RMS. could also rewrite this another way and say that it is 3 times RT divided by the molar mass in kg. In this particular case, we want to use the R that is for joules. And we'll notice that as the square root of the molar mass increases, these things are becoming heavier, and the Vrms, velocity, is going to decrease. So this is in the denominator there, so it will become slow and heavy. Now let's tie the velocity and the kinetic energy back together by saying that we can also say the Ke average is equal to 1/2 times the molar mass in kg times Vrms squared. 1/2 mv squared. That's quite interesting. And of course, the Ke average, we can rewrite this as 3/2 RT. And we'll notice something very important is that the kinetic energy only depends on the temperature of the gas. There's only RT there. It's the only variable that matters for kinetic energy. So temperature is pretty important for gases. I'm going to try to fit one last thing in here, which is the van der Waals equation, simply a more formal, correct version of the PV equals nRT ideal gas law. So we'll be able to use it in any situation. So we go P plus, and we're going to have an A variable there. And then we've got N divided by volume. We're going to square that. So then we're going to multiply that by volume minus N times this B, and close that off. Set that equal to the nRT. And let's see what this is really trying to say. Well, again, N is going to be the number of moles. So, this is something which was from the previous situation as well. The V is always going to be the volume in liters of the container that this gas is in. And then we have this A and this B. So the A has to deal with the intermolecular forces of what's going on inside the gas. Remember, we kind of talked about that over here, because the ideal gas law works with the kinetic energy is really high, but if we account for the intermolecular forces with this variable, then we can use this. And also for the B is going to account for the size of the particles of the gas. And so kind of similar to what we were here with this, the particle size had to be a certain very, very small compared to the container of the volume. We don't have to worry about that anymore because we have this particular thing. And both of these variables can be found looking at a list. It's called the van der Waals constant list. So you don't actually have to do any calculations there. These things are given to you just like the R. And so this is basically everything we need to know about gases.